I'm Kevin Jordan. I'm with PCD Sales. Let's see how I go forward here. I'm with PCD Sales. We're known as PCD Sales down in the Texas area, process control dynamics in the Rocky Mountain region. We're a manufacturer's representative for HMI and SCADA products. We're kind of you see our 3 drops there. We kind of have main interests in the oil and gas, water, wastewater, and critical infrastructure areas. So we're kind of from, the wellhead to the enterprise level on just about all of our products that we do. And we specialize in open standards, OPC-based products. Patrick DeCesaro is with us, and Patrick is one of our integrators that's in our network of integrators that we use for integrating and completing the projects that we have out there. So Patrick's out of the Lubbock area with DeCesaro Integration Services. So much like real life, as a sales guy, I'm going to kind of set the stage, paint some broad strokes, kind of give you the background of this project that we did here for Nucor Steel with OPC UA. And then Patrick's going to come in and fill in the details and kind of fill in the holes where I left them out. So a quick overview. So Nucor is one of the largest mini mill operators in the U.S. It's kind of an iconic, the steel manufacturing industry is kind of an iconic piece of American history. Kind of put it up there with the automotive industry or the oil and gas industry or whatever else. So it's kind of a neat project that was completed here. They recycle 1 ton of steel every 2 seconds. That makes them the largest recycler in the U.S., which is a very impressive stat. They entered the steel industry in '68 with their first mill in South Carolina, and they now employ over 20,000 employees. So they're really moving and grooving in the steel manufacturing facility, which, by the way, has kind of had a decline over the past few years, as you guys know. So they're really up and moving, and we'll talk a little bit about how we helped improve their quality and process. They built their first Steckel Mill in '85, and it now produces 1.2 million tons of steel coil, discrete plate, and cut-to-length plate. So they have several products that they produce here. So you can see the coiled, the discrete plate, and the cut-to-length here. They're finished products. So some of the products in action, we start off with just scrap metal. That's how they have so much recycling, and it ends with the whole steel plate, cut to length, cut to dimensions, the exact size that they want for their customers for the products they're creating. We were talking about this earlier. We would be surprised if John Deere didn't use a lot of steel that came from these guys at some point. So about 75 to 90% of the finished product is created from scrap, which I think is a very impressive number there. So let's take a little look here at where some of these products are used. So once it's cut to dimension and size, 2 of their major customers would include Texas Tanks and Gulfport Yachts. Tanks of any size, from obviously a huge one here to all the tanks that we used in the oil and gas industry out there in the field, and then performance yachts. So we'll see these guys all over. Those are just a couple of samples of ones that they use. Trinity Yachts out of Gulfport, Mississippi. Let's talk a little bit about the process that we have here, kind of from beginning to end. We've mentioned a couple of times that 75 to 90% of the finished product is made out of scrap for recycling. So but whenever they put this together to create a batch of steel, it's a very precise amount that they put in there depending on what the finished product is. So the thickness, the quality of what it is. So it's very finished product there. They take this batch and they put it into a big bucket, basically. And I have some notes here. I want to make sure I get these correct. But they add some iron pellets here to create a composition that's exactly what they need. The bucket drops it into an electric arc furnace. And so it goes in there, it's lowered in there, and they drop electrodes into this arc furnace. And at this point, they give it a slight charge, a charge of about 105 megawatts to begin to melt the steel. Little charge. It takes about 45 minutes, and it gets it up to about 3,000 degrees to create a molten steel. Now, I've heard this described as a train carrying a load of volcanoes and earthquakes. It's very noisy. It's very loud. It shakes. It's an impressive sight. But what's pretty cool about this is after about 45 minutes from one of these batches, you can create 150 tons of steel. So it's a fast process that produces a lot of yield. Once they've gone through the electric arc furnace, it goes into a ladle. And essentially what they're doing here is they're monitoring the chemistry of what they've got. So they can add or subtract alloys to create the correct chemistry for what they need. They can take a look at the chemistry, the cleanliness, the temperature, and monitor all these things and adjust it accordingly to make sure that it comes out the way they want it to do. It moves into, at this point, a Tundish, which is basically a big reservoir. And what the reservoir does is it drops it into these molds, and these molds can adjust width on the fly. So now they can create these bars of steel in different widths out of a single Tundish, so they can create to order, basically. And that's kind of a unique thing to Nucor here. So once they go in there and they go into these, they produce these bars, and it comes out the size they want it. They've got to reheat it again. So we start reheating again. We go back to a hot mill. We get it up to about 2,250 degrees, and at this hot mill, we begin to roll it. We get to roll it out. And another thing that's unique to Nucor is that during this process, they can roll it and they can finish it, and kind of create it all in one step, where it usually takes a couple of steps for other guys. So they have some unique processes there to help expedite their process control. So we've heated it up, we've rolled it out, now we cut it to length in this hot mill. And once we get it to the desired length, we roll it and get it to the desired length, they cool it down and they coil it. So at this time, it's coiled, they can weigh it, label it, and ship it out to their customers as a coiled product. Or they can also take it and they can heat it again into another mill, into a temper, and they can roll it back out, and they can create the exact desired thickness that they want, anywhere from 3/16 of an inch to an inch thick. And they get those into 1 or 2% tolerances, so they can get a really tight tolerance for the customer desires. So as you can see, there's a lot of things that happen here, a lot of energy used into creating the steel, and a lot of thought that goes into the quality that they produce. So that's kind of a nutshell of what Nucor does and how they do it and the process control. Some of the issues that they had on the project were there was no control over the control system communication. And when we say no control, we mean no control. Basically, everything was on one network. So you had your process control, you had your business network, you had social media, anything else you wanted on that network was basically going. So it needed some work. There was little to no security as well on their process network. And they had a legacy HMI system. Now, the legacy HMI the slide states it was at the center of many issues. It wasn't an issue with the product itself. It was more of an issue with how it was being maintained and how it was being rolled out. As things grow, you kind of throw these things out there and you kind of haphazardly put them in place, and then one day you wake up and you say, wait a minute, this is not working, we've got to make some changes. So afterwards, once we were done, the communication was streamlined, multi-tiered redundant SCADA solution, optimized the control network, and we implemented security. And OPC UA is the base of that. So with that, I'm going to turn it over to Patrick, and he's going to talk a little more about how that was implemented.
Thanks, Kevin. I'm just going to continue real quick without talking much more about myself, just given some time constraints. So Kevin mentioned briefly kind of the legacy HMI system that was in place. It's something that kind of grew. This mill was built in 1985, and as automation scaled up, new systems were kind of put in place without a lot of planning and architecture going into place. They figured they had one standalone HMI that worked really great. We could go ahead and expand that, and that works okay for a little while. And what we got to was a much more better designed architecture that really optimized communication and took care of a lot of the problems that the initial system was causing. So kind of an overview of the challenges we were facing. The control network was not always designed or maintained, and This was before Nucor had came in and purchased this mill and started running it. Nucor has a philosophy of continuous improvement. And once they took over the business, they really started to drill down and figure out where all the problems were. The control network was overexposed to the business network, and access to the interwebs was just too easy from anywhere. When you're running your process on an HMI at the same time that you're streaming internet radio, that could lead to some big problems. So what it resulted in was valuable quality metrics not getting to the right people at the right time. Quality engineers, metallurgists, they weren't getting accurate, complete data to be able to measure the quality of the product. And the lack of security created a lot of problems as well. So what were these problems with the network architecture? When you have an HMI or SCADA system, you also have an I/O server that communicates to your PLCs or your control systems. And you could add another HMI, and it might have its own I/O server on it as well, and that starts communicating to the PLC, opens up another communication channel. So you start adding these on, and you're adding more load to that communication module on your PLC. Works okay for a few systems. You have a dozen or 24 of these guys trying to communicate to a legacy PLC. You start having lots of problems. When your operator starts trying to run machinery from the HMI, you have huge delays. And what's an operator do when he hits a button on the HMI? Does he sit and wait for something to happen? If nothing happens, he wants to hit it again and again. And what we were experiencing, it was pretty common to see a 4-second delay between operator action and something happening in the PLC. And the legacy PLCs have some constraints. It's older technology, and we found that PLC 5s, after 4 connections, the performance is severely degraded. There were also a lot of default settings in the PLC to PLC communication, even with the newer technology, where block read and writes were set to 50 milliseconds, and we had to educate the technicians that were doing programming in these control systems that we really needed to slow that down to speed it up. And it seemed kind of counterintuitive to some of the folks, but when you're pounding PLCs for communication at 50 milliseconds, it starts to slow everything down. So that architecture also made application management a big challenge. There was no version control, so you might have different versions of the same HMI on different systems. I mentioned it was common to see 4-second minimum update rates. Sometimes that could be as slow as 12 to 15 seconds. And that could be a serious threat to not just your product, but to the safety of your personnel in an environment where you have those high-powered electric arc furnace and 2,800 degree steel. So what we did, we kind of took a step back, redesigned everything, made a plan to. They had already replaced about half of the legacy PLCs with newer technology. We made a plan to methodically replace the rest of the legacy PLCs over time. Most of these were already reaching the end of their life cycle, so it fit in with our strategy. We created a multi-tiered SCADA solution, and a big part of that was the adoption of OPC DA and OPC UA as the primary communication path. Also, you can imagine when they were putting in the new systems, they thought they had a lot of redundancy. You know, one system goes down, they still have an I/O server on their on the HMI in the room next to them. As part of our SCADA system, we implemented redundant SCADA servers, redundant OPC servers to reduce any potential downtime, and also to help with patch management, updates to our software. But really, what the end result was streamlining communication to our PLC network, and really speeding up and optimizing our communication. So this is just kind of a generic drawing of our architecture, and it's definitely scaled from this. But down here you have your control network. We have redundant OPC DA and UA servers. We put our historian collectors on those same machines because we wanted that data collection to happen as close to the data source as possible. And those historian data collectors can store and forward data up to our hyperhistorians and SCADA system. We put in several sets of redundant servers in the SCADA servers in the different areas of the plant. Kevin went over the different major processes of the steelmaking procedure, and each one of those areas has its own set of redundant SCADA servers. And from that, because we really streamlined the communication to the PLC level, it really opens up our access on the client side to HMI's MES system. We're able to generate reports quickly for our quality engineers and metallurgists, supervisors, and just performance has really gotten a lot better. So I kind of talked about the benefits of the changes we made, and really we're helping them to make steel better than they were before. Here's just I have a few examples of what our SCADA system, what our HMIs look like. This is for the electric arc furnace, and just shows a picture of the furnace, and this is in a shutdown state, so we don't see our electrode over here in the furnace melting steel. Here's an image of our caster overview screen. We have a 3D real-time. All these positions of this turret and these Tundishes come from the control system. And someone asked me if 3D graphics in an HMI really provide any value. My argument would be that yes, it does. This means a lot more to somebody when they can't see that. When the mill shut down, when the caster shut down, they could see all this fine out on the plant floor. When it's running, there's so much steam and dust generated in this place, you can't look out the window and see which Tundish is in which position. And having that image means a lot more than words or numbers on a screen. So when there's an accident, they're able to respond a lot faster and a lot more properly than if they didn't have that. Here's an image from one of the cut-to-length HMIs that the operator sees. He's able to see quality metrics in real time. That's going to help him pull any secondary plates off the line for further inspection or for reprocessing. He also is able to see a lot of real-time camera images from all angles of the process. And these operators, when they're stuck in a pulpit for 12 hours, they can't go out and view the process at the same time that they're operating it. So having this visibility is vital for them to run lean and produce high-quality steel. So it doesn't just get used in the process. The environmental department is also using this data. We generate a daily report that shows the environmental engineers exactly where all the water usage is consumed around the plant, and they're able to identify where they might have leaks at different parts in the process, and that's saved them a lot of. I think they're spending somewhere around $150,000 a month on. That's how much their water bill is. They use a lot of recycled water, but also city water, and 90% of that bill is coming from the city water. So one of the other problems that we needed to address was the security of the control network. A lot of the sessions at this conference have been about control system security. So we've learned that it's not just an IT problem. It's not just a control system group problem. These different units have to work together to solve the problem of security. Control groups need sometimes the expertise of IT to help with that, and IT department needs the control groups to help the IT departments really help and not help by sometimes disrupting the process if they roll out security policies that can unintentionally prevent access to the data that operations and quality needs. And so part of that is an effective defense in-depth approach, which involves everybody in the organization. So there's several different methods that need to be used in that defense in-depth philosophy. One is data security, and choosing OPC UA has been a part of that strategy. The server-client relationships with OPC UA use the certificates, which Jeremy mentioned, that get registered at each machine, ensuring that the OPC servers aren't being asked for data from unauthorized machines. Network security has certainly been an important part of that. The segregation of the networks to separate the process machines from the rest of the business network. And the IT and control groups are continually taking additional measures to make the plant more secure. We also have a lot of application security with our SCADA software. We're able to leverage both Active Directory and application security of our platform, and we're able to get very granular with that. And with read-write access, read-only access, you could isolate communication to specific machines, specific users, and even prevent specific users from even reading specific data points if we need to. So that gives us a lot of the proper access to the right data. This is in a supervisor's office, and they're able to see real-time quality metrics, what's happening on the process when we're in our office doing administrative duties. So what do we gain from OPC UA? Our SCADA system, the platform services from Iconics, is OPC compliant and certified. And the secure communication of OPC UA and DA, we're still using DA for parts of the process, are integral to helping us be more secure. One thing that we've talked about implementing, and we're just in talks about it now, is the use of complex objects. I think at some point, Tom could probably talk a bit more about compliance testing within the OPC UA specification, what that involves, and what that means for various software vendors that are using OPC UA. So one of the biggest benefits that we see is the security of the OPC UA platform. Done through authentication, authorization, the confidentiality of data. So through certificate exchange, we're able to verify that the requester of the data is who he or she says she is. The certificate authority it issues the certificates. So one thing I wanted to bring up was they're using this on mobile platforms within the plant as well. Just a couple weeks ago, I was out at site, and we implemented this. This is a display built for mobile HMI. They put in a slab slitter. Kevin mentioned that the caster will adjust width on the fly, and so what you end up with is slabs that are wider at one end than they are at the other end. And so to help improve their yield, they want a perfectly rectangular slab. The slab slitter will trim off the excess steel. So the slab slitter is not inside; it's out in a slab yard. And there's a picture of it right there. I couldn't get a photo of it with it running at the time, but it's in full production now. OPC UA has really helped us get data quickly to the right people at the right time. And during the panel, I'd be happy to answer any more questions about what technologies we're using or about the steel process. Thank you very much.